to produce current from the solar cell, right? Now, so these carriers, to increase the number of carriers, we require doping. And also we know that the absorption of the light will create some more number of carriers. And then they will move here and there due to maybe electric field or maybe due to the difference in the concentration. Uh, and these are based on the two phenomena, drift and diffusion. And meanwhile, they move. There is a possibility that they can recombine with the holes, or minority and majority can recombine, and it may or may not ultimately contribute to the current. So whatever we have done in the last chapter or so, everything is qualitative. Okay, so we know the process of whatever is happening. However, that was the basic part. And what we are doing this now, you can see carrier concentration and distribution. Okay, so we know that there are carriers. So, but we don't know where they are, and we don't know what will be their concentration. So, if earlier one was the qualitative analysis, so this you can say that it is a quantitative analysis. And why we do that? Because ultimately for the device we need current and voltage characteristics, and that depends absolutely on the availability of the carriers and their numbers. So obviously this becomes an important step so that we can ultimately determine the carriers, and we can determine every function related to the device, and we can find out efficiencies and whatnot. Okay, so this is the fundamental. And of course, there is other thing called as optimization. So when we make PN junction, fine, great, it will work as a solar cell, but that won't be efficient. So what can be done such that this number of carriers are increased, and rather more and more carriers take part into the conduction. So again, there will be some fundamentals over here which you have already learned, but then slowly what we are building is that some equations that will ultimately lead us to the current equation for the solar cell. Okay, so now let us start talking the important part, that is DOS, or a density of states. So already we have talked about these states. Okay, so when there are infinite number of atoms which are coming near to each other, we have a band of the states. And then we have to also talk about where these carriers are and where they will be sitting. Okay, so device is a state, and Fermi level is, of course, we are going to see. So what will be the impact of Fermi level, and how it can help us to count the numbers. Okay, so let us start with one small concept. We know that electron has got a mass. However, when we talk about electrons in semiconductors, we don't take mass. However, we take effective mass into the consideration. And this effective mass is bit more. And why it is happening? Because the normal mass, when we talk, it is of the electrons in free space, when there is no hindrance to the movement of the electrons. But whenever it is in the lattice, it is going to experience, the movement of electrons is going to experience some forces which is going to influence the motion, the movement of this electron inside this lattice. And it is happening because of the presence of other charge, because this can get attracted to the protons which are positively charged, or it can get repelled by the negative charge. So these forces account for the what you can say distraction of the moment. In a simple sense, you can imagine again the concept of mobility, right? I mean, mobility, what we said, that when the road is free, you can go at the speed of 100. But when it is traffic, hardly you can reach 10, 20 kilometers per hour. So that was mobility. Okay. But now you feel it in terms of mass, that you feel heavy. So when in a sense, when you are moving slowly, it means what? Heavier you are, you will move slowly. So that way you can relate with this. So instead of using m, we are using m star for the effective mass. So obviously for electron as well as hole, there will be this effective mass, so that when we take into account whatever the force is, the force equation will become m star into a instead of m, and then obviously m star is the effective mass. So this particle mass is obviously there, plus the effect of these internal forces. So that is the total. So in this is a virtual thing. Okay, this is what it experiences because of these forces. Okay, so already we have discussed this Pauli exclusion principle as well. Just let me repeat that there could be hundreds of quantum states. However, in a single quantum state, only one electron can occupy. So in other sense, it is also a pigeonhole principle. I think you have learned the Hund's rule as well in your chemistry, that in one box you can have two electrons with two opposite spins. Okay, so one state can now occupy only what you say, one state, one electron. So obviously this the carriers are going to contribute to the conduction process, and that depends on number of available states. In a simple sense, let us say we have got 20 seats. There are only 20 electrons can sit over here. So obviously only 20 electrons can take part into the conduction, right? But suppose we have got 50 seats, we can accommodate more electrons. So obviously we will have more electrons available for the conduction. So and also we have said that whenever these atoms come close together, there will be splitting of the energy levels, and there will be some allowed and forbidden energy levels, and that is what actually makes the discrete. But whenever there are too many such a energy levels, it almost becomes a band, because ultimately it has to accommodate so many of electrons. So the point is, this density of these levels, that is what we have to determine. And these states, quantum states, how many states are available, that what we call it as density of state. And this is important because it is the function of energy. So at a particular state, what will be the energy required for the electron and the hole to occupy that? So from this, once we know the energy, once we know the concentration, we can find out the number of electrons. So for calculation of density of state, you can do this simultaneously with me. By the way, pardon me for this particular chapter presentation, because there will be some text over there, because uh, uh, to explain, I need to write few things, and so that the slides will be also handy for you, so that it will be a kind of notes for you. Okay, so that's why sometimes on some slides it's too much of text, but please bear with me. It is for our good. Anyway, so this density of states, that is what we have to determine, and for this we will use this formula as it is. Actually, you might have derived this in physics, but that is not our objective. So I'm directly borrowing this. So this much from using this particular formula, we are going to find out the density of states. Okay. So now another thing is about the energy momentum relationship, what we are using to describe the energy, right? So on y-axis it is energy, this is momentum. Now I think I told you that we draw the band something like this, right? This like this. Then obviously for schematic presentation, we simply say this is conduction, this is valence. And at that time I told you that actually these are two simple representation of what exactly the band diagram looks like. So here you can see the actual band diagram, and you can see there are troughs and valleys in the band diagrams, and that's why when we define the energy band gap, it is from the highest point in the valence band and in the lowest point in the conduction band. Okay, so now our concentration will be on this particular part. So you can see here this part, and now the right side, this is for silicon. So in silicon, as it is indirect band gap, you can see that the minima and maxima are apart, they are not aligned. So this part and this part, if you see, they look like a parabola, and that is what the approximation that we are going to do. So you can see that if this is the part of parabola, we will have so many states over here, and at every state we can have electrons. Anyway, so this relation we have already seen between the momentum and the energy. So this, as I said, this can be approximated as parabola. This energy expression now can be written in terms of EC. So if this parabola we are talking about, for describing E, then E will be equal to this lowest level is C. So E plus EC, E is equal to EC plus whatever the state over here, and that is given by this. Okay, so obviously we are using now M star and N stars for electrons. So initially we will determine this for electron, and then from the similarity we can figure out what will be the equation for the holes. Okay, so let us rearrange this. So it will become E minus EC is equal to this particular constant. Okay, fine. So now you can see here, this is what we are trying to do. So this basic equation we are going to use, and what we want is this energy. So you can see here, number of density states is proportional to what is the energy. So in this general form, we can substitute this E by E minus EC. Why? Because this is the extra energy that a particular state will be having above that conduction and conduction energy. And then after substituting, what we get is the GC of E. Obviously this expression is valid for whenever E is greater than EC, and this gives us the density of state expression. So you can write down this expression. We require these expressions later. So such a important expressions, at least you should write down simultaneously. Okay, so please write down this expression. So obviously you can see that if the difference between this E and EC decreases, obviously number of states are going to decrease, and vice versa is true. When the difference is higher, we get more number of states, and obviously we get possibility of more electrons. Electrons would be there. Okay, so this is a DOS for the conduction band or for electrons. So similarly, we can go for valence band, and now you can use, instead of Mn star, we are going to use Mp star. The concept remains the same. Okay, so again the parabola approximation can be done, and then this expression, it will become Ev minus E, and so here instead of E, now you are writing Ev minus E. So that is the energy we are talking about, and obviously this will be, expression would be valid when the E is less than Ev. So your energy in valence band cannot be higher than the Ev energy. So this is the expression for GV. So absolutely parallel, and you will see that in this whole chapter we will have such a parallel expressions. Whatever is for electron, with minor changes because of the property differences between electron and holes, will be applicable for the holes, and you can derive the expressions parallelly. Okay, so obviously we will not concentrate much on holes derivation, but I have given in the slide, so you can figure it out. It's absolutely parallel to this. So this expression also you must have noted. So these are the two expressions that we have for the GC and GV. Okay. Now let us talk about more. So we have got, you can, from the previous expressions itself, you can understand that we are talking about the energy either higher than EC or lower than EV. We are not at all talking about any energy which is in between this EC and EV. Okay, and that is what we have even discussed previously, that there cannot be a state in between the conduction and valence band, because then that is not meaningless, right? That is how we have defined the band gap itself, that that is the minimum difference or distance between the two bands. So this phenomena is called as the forbidden energy band gap. Okay, so there cannot be anything. So if we try to now plot of this density of state, whatever we have derived versus the function of energy, it will be something like this. Please draw simultaneously with me. Okay, please draw simultaneously with me. So you can see that on y-axis we have got energy, and then obviously density of states over here. This particular development we are going to use frequently for intrinsic and extrinsic semiconductors in the coming slides. So better you do it along with me. So now on energy, we know that these are the two bands EC and EV. Again, I'm drawing it flat because it's a schematic diagram. So there cannot be anything in between. That's the forbidden area, restricted area. So now, of course, we know that this expression, what we have derived, is the approximation of parabola. So obviously, when energy increases, this GC should increase in parabolic term. So we have this expression, and vice versa, or in absolutely opposite or symmetrical manner, we get the what you say curve for the GV as well. So obviously this G of E will be 0 in this in between the two when the E lies in between EC and EV. So there won't be any state over here. Now you can see that those two expressions are more or identical, especially that constant. Okay, so that constant consists of this mass of the carrier, either electron and holes. So normally we assume that the mass of electron and holes will be equal. Okay, however, exactly it is not. I think I have told you previously as well. Mass of electrons and holes are slightly different. Okay, but just for sake, if we are if we neglect that minor difference, what will happen? Then we can understand that if that is equal, then the whole that one term becomes constant, and it absolutely proportional to root of whatever the difference. Okay, so you can see that if these two masses are equal, then there would be a point exactly in between EC and EV, about which this whole diagram would be symmetrical on the upper side as well as on the lower side. And from the expression, it is evident that this is exactly in between. So if we want to calculate the energy or energy level of this, it will be EC plus EV divided by 2. Okay, so this particular fictitious level, okay, again it's virtual, it actually doesn't exist, but just for reference, just for using that symmetry, so we can say that this particular energy level is the mid gap energy level, or E mid gap. Okay, so with respect to that, we are going to talk about the Fermi level, existence of Fermi level. Fine. So this is all about the density of states. Now there are many distributions which are used in semiconductors or in the particle physics. Okay, so let me just give you the brief. So one is Maxwell-Boltzmann one. So here what happens is the particles are distinguishable. Okay, so you can number them 1 to n, obviously. So there is no limit on the number of particles allowed in each state. So this particular distribution is used for the behavior of gas, because you cannot use it for semiconductors. Why? Because we cannot have the particles with the same energy state, because poly exclusion principle prohibits it. Okay, so this is used in the kinetic theory of gases and all that. Another one is the Bose-Einstein function. So now particles are indistinguishable. Here it was distinguishable. So here these particles are indistinguishable. It means they are absolutely same. Their behavior is absolutely same. So let us say, for example, photons. Okay, so when we try to what to say display the this distribution of photons, we can use Bose-Einstein function. But what we are going to use is called as the Fermi-Dirac probability function. So that's why the name of the level, energy levels, are Fermi level. Okay, because Fermi-Dirac distribution is what we are going to use. And interesting, it is the probability. So again, these are all quantum mechanics things. So obviously, we always talk about the probability. So when we say that the probability is half, it means only the probability. It's not that always there will be a particle. There is a chance. There is a 50% chance that the particle will be in particular place. So again, particles are indistinguishable. Actually, what I mean here is, if you take two electrons, they are absolutely same, right? So if you interchange them, there is no difference as such. One electron or other, it's the same thing. Okay. However, the important point is, here only one particle is permitted in each quantum state. So that's why every arrangement would be, although electrons are same, but we have got several possibilities coming over here. So that's why for semiconductor particle distribution or carrier distribution, this Fermi Dirac probability function is what we are going to use. So what is this? Pauli exclusion principle we have already discussed. So you can see that there are quantum states from 1 to 3 up to some GI ways. Okay, so now obviously there are GI ways of choosing where you can choose the first particle, here or here or here or whatever. But when you go for the second particle, you will have one less number of choosing the ways, because now one is, let us say this is occupied, so you have got now GI minus 1 ways. Similarly, you can go on doing it, and you can say that as you proceed to n, we will have GI minus n number of ways. Now, so if we have got such a n number of particles at, so this I is for the ith energy level. So what we can write down this arrangement in terms of the way how we can arrange, in how many ways we can arrange these particles, can be given by this. Okay, so now the point is, we have already said that these are the electrons we are talking about. So these are indistinguishable. So suppose we interchange, let us say from 1 to 2, it is not going to produce a new arrangement. Okay, the after replacement, even the arrangement will look like what it was previously. So that's why the independent ways of realizing whatever this distribution could be, this one. So this is what the exactly distribution is. So we can go on arranging it, and we can find out the total number of ways. The point is that whatever this statistical distribution, this formula we are not interested in. However, this particular distribution, if we want to what you say, write in terms of our energy level, so this becomes the function, and this we can call it as the distribution functions for the energy level. So you please write down these expressions. So you can see here, obviously it depends on the energy, because that is what we are talking about, and then it is with respect to some energy level denoted as EF, which we call it as the Fermi energy. And obviously temperature is going to affect this number of carriers on a particular state. So KT is also there. So if you try to plot these two expressions, the result would be very much similar. Then this N of E is the number of particles per unit volume, and then G of E is the number of quantum states which are available in a particular unit volume. So you can see that this is what the probability we are giving. So how many particles are there, and how many states are available for us. Okay, so if there are 100 states and only 50 particles are occupying the seats, then we can say that the probability is half. Okay, so this basically is a probability function, or probability distribution function. Okay, so we are going to treat it like that. So please, I think you have noted this particular expression, because whatever the expression, we are going to try to find out the physical significance of it, or how it is going to help us to understand how exactly the distribution is going to be. Okay, so remember, we want carrier concentration, and for that, if we can find out the distribution, and then if we can multiply by the density of states, we get the number of concentrations. Okay, so we are into the second part of this. So this expression we are going to evaluate. Okay, so again, I'm writing it for you. So now this distribution of electrons or any carriers will be over the range of allowed energy levels, and these levels are now given by this particular functions. So it tells us how many states are there, or it gives us the probability that a particular state is occupied by the electron which is having a particular temperature T. Okay, so already I have said that it can be defined as the ratio of field quantum states to the number of states which are available over here. So with this expression, now we can have several extreme conditions or typical conditions, what we can say. So as I've said, two important parameters which are going to affect the distribution or outcome of this equation. So first one is obviously the energy. What energy? Suppose we are taking any carrier, how much energy it has, and also at what temperature we are talking about. Okay, so let us start with T equal to 0. So there is no thermal excitation whatsoever. So obviously, electron doesn't possess any energy, and they are right now in the lowest possible energy states what we can think of. Okay, so at this place, all the electrons having energy below this Fermi energy will be there. So you can see here the energy is less than EF. That is what we are considering right now. So when you substitute this T equal to 0 and you assume that E is less than EF, the so 1 upon 1 plus this expression, correct? So this expression reduces down to 0, and then 1 upon 1 plus 0, so the probability becomes 1. So what does it tells? That at T equal to 0, and when the energy of the electron is less than the Fermi level, you will find out that the probability of finding the electron will be 1. So at T equal to 0, all the electrons will be at lower state than the Fermi level. So you can see that there is a very harsh drop in the probability. So it was 1, and then now it is suddenly 0. Okay, so now next what we can do is we can have what you say more temperature. So if we increase the temperature, what is going to happen? Some of the electrons now gain extra energy, and then there is a possibility that the electrons try to move on this side. So you can see here that some temperature increase, let us say T equal to T1, which is higher than, let us say, T0. So some electrons will move up above the, what you say, valence band. Obviously they cannot be in between the conduction and valence band, so they must be somewhere in the conduction band. Okay, so but some electrons, so there is a possibility. So if we increase the temperature further, what is happening? The energy is further increasing. So you can check with our table now. So still let us say T is equal to 0, but E is greater than EF. So at that time the probability is 0. Already I have explained. Now when you increase the temperature, and as I said, there will be more and more electrons which are going above the EF, so that probability will increase. And the typical case is that when E is exactly equal to EF. Okay, so now what is happening is, if you substitute this, this expression comes out to be 1, and the probability comes out to be half. So when T is greater than 0 and your energy is equal to EF, the possibility is that either the electron can be here or it can be here. Okay, so that's why we have drawn a 50% probability case over here. So this tells us that what could be the probability depending upon what is the temperature and what is the energy which is which that carrier has. Okay, so what are the conclusions from this particular graph? First of all, so probability of energy above EF obviously will be increasing as the temperature increases. And that is evident, right? Because we know when temperature is increased, carriers get the energy, electron gets the energy, and then there is a possibility that if the energy is sufficient, they can go into the conduction band. Okay. So obviously the vice versa is also true. When the temperature decreases, the probability of states below this EF is going to increase, right? Now, other thing is the probability of a state, let us say, at a small distance dE. So this can be any distance. Now this distance we are measuring in terms of energy, because that is what our y-axis is. So when we talk about the probability, the if some energy level is above here, let us say this energy, and then we have got another one which is just below. So the distance, this distance and this distance from the EF is exactly same, then obviously the probability of the electron being either in this state and this state will be absolutely equal. Okay, so that is the equal probability, and that is why if in earlier graphs, if we have plotted the probability of the Fermi level or probability of electron occupying a particular state, it will be absolutely symmetrical when we take whether there is a probability that it doesn't occupy this particular state. So that is where that symmetry is it will be useful for us. So for I can show you here. So if this is the probability function at some temperature T, then this is what we are drawing, right? So we have got some probability that it will be above EF and some probability that it will be below EF. Okay, and this is that halfway mark. Okay, so now if I plot 1 minus f, obviously it will be symmetrical, and obviously that point about which it is symmetrical is the EF. Okay, because that is what our reference is, that is what our benchmark is. Now, we have already seen that the expression or the expression for the distribution is 1 plus 1 upon 1 plus this particular expression, right? So now what happens is we are not going to, at least in the semiconductor applications, we will not be dealing with the cases where temperature is 0 or very small temperatures, right? Normally, we will be talking about the temperatures, room temperatures. Okay, so it will be 300 Kelvin or so. So what happens is at that particular temperatures, this E minus EF is very high as compared to even that even at T equal to 300. Even at 300, the E minus EF is quite high compared to the KT. Okay, so in that case, this if you take this ratio, KT is very negligible. Okay, so you can say that this exponential term in the denominator is quite higher than 1. So that's why this 1 can be neglected. So you can have 1 upon this, and then you can approximate. So your approximation will become this, so that it will be easier for us for the further calculation. Okay, so in most of the time we are going to assume this particular approximation. So here the probability function is approximately equal to exponential of minus E minus EF by KT. So you can write down this particular approximation. So this will reduce our calculations. Okay, so you can write down this expression. So that is what we are going to use in the few slides which are upcoming. Okay, so slight approximation. E minus EF is quite higher than KT, so 1 is neglected. Fine. So now let us combine whatever our density of state and EF, the concept of the Fermi level which we have obtained. Now this particular diagram I have rotated. Okay, so earlier E was the vertical y-axis. So you can see that this is the parabola we are talking about. Okay, so now this curve is obviously given by G of E, that is the density of states. And as I've told you, these are the number of states. Now suppose I multiply this by the probability that the electrons would be there. What I'm supposed to get? The number of electrons, right? So the number of electrons in a particular system, let us call it as N0, that should be equal to the area under the curve of GC. So whatever this area under the parabola is going to give us the number of electrons. And what is this curve? That is the density of states. And till what level the density of states are occupied, so that is what going to determine the limit. So it will be between the 0 and EF. So if we integrate this to find out the area between 0 to EF, we will get the total number of electrons. So you remember these are the states, right? Vertical lines, these are the states. So at every state there will be the electron here. So in a simple state, in a simple sense, we are going to add up all the states, multiply by the probability, and then what we get is not probability. We integrate this density of states from the 0 to EF, because that is what the probability is, and then we get the number of electrons in the system. So now you can understand that we know what is the density of state, that is the availability. How much is how much is the area which is covered by that density of states, and then we get the number of electrons in the system, and that is nothing but the number of carriers which are available, which will be taking part into the current. Okay, So this is how the Fermi level would be important for us to tell us whether to give us the probability of having an electron or a hole at a particular level. Okay. So now whatever these concepts of density of states and Fermi level, what we have learned, now we will try to apply it for the intrinsic semiconductors. So here we can talk about the equilibrium distribution, right? Because this is intrinsic, we have not doped anything, right? So obviously, when we talk about the distribution of energy in, let us say, in conduction band, similar thing can happen also for the valence band, right? So distribution of electrons in the conduction band, when we are talking about conduction, then it will be the density of allowed quantum state in the conduction band, that is given by the density of states, and the probability that the state is occupied by the electrons. Okay, so this is the probability, this is the density function, and this will be the distribution of electrons that we have, and the total concentration will be if we integrate it in that particular volume. So similarly, when we want the holes, we know that whenever an electron is generated, simultaneously there has to be a creation of holes. So if the probability of electron in a state is some x, then obviously the probability of the hole being in a particular state would be 1 minus x, and that is what we exactly do. So f of f and 1 minus f of e, okay, f of e and 1 minus f of e. So that is the probability of that is a distribution of holes in the valence band. Okay, so we can multiply it by density of states. So obviously, again, we can integrate and we get the total number of electrons or electron hole concentration per unit volume in the valence band. Okay, so you can see that these are absolutely parallel, and then we are using the symmetry to find out things. Okay, so if we have to find out that electron and hole concentration, we need to find out the position of Fermi level with respect to the bottom of conduction band. So it means if we have got this EC and if we have got this EV, we have to find out where that Fermi level is going to sit. Okay, so let us consider one intrinsic semiconductor. So at T equal to 0, what is going to happen? That there is no energy for the electrons, so you can see that the valence band will be filled by all the electrons. I mean, they have not left these valence bands. They don't have the energy to go up. Okay, so at that time EC is absolutely blank. There is nothing over there. Everything is absolutely here. 100% carriers are still in the valence band. So obviously, the Fermi level, because now the probability is 1 the probability of finding the carrier is 1 in this valence band. Obviously, there is nothing here, that is 0 over here. We can easily assume that this Fermi level, now Fermi energy, must be sitting somewhere between the EC and EV. Okay. Now what happens is, suppose we are increasing the temperature now, which is above 0 K. What will happen? Some electrons will gain some thermal energy, and if that is sufficient, that they can cross this barrier or this forbidden energy gap, what is going to happen? This electron is going to jump to the conduction level. Okay, so let us say we have promoted electrons. So as this electron goes into the conduction band, we will have one hole which is produced or created in this. Okay, so obviously at intrinsic semiconductor, there is always, as I've said, EHP. There is always a pair of carrier which is created. So at any point of time, in the semiconductor operation, electron and hole, the number will remain same. So there will be always, it will always occur in the pairs. Okay, so that is what we have. So again, we can go back to this curve. So you can plot simultaneously. Now we have got y-axis as E, and we know that the G is the density of states. So now we know that the probability, it's a probability, so the limits are 0 to 1. Then we can draw EC and EV. I think you are drawing simultaneously with me so that you can understand how exactly these things are drawn. Now we know the density of, we know Fermi level, it should sit somewhere in between. Qualitatively, it should be the mid gap, right? It should be in between. We have got this GC and we have got GV, and that is symmetrical around this midpoint over here. So next, if we want this Fermi level to be here, so now you can see that the probability that the Fermi level would be occupying this state, it depends on what is the energy over here. So if we want how many electrons are in the conduction band, so this is the area that we have, right? So if we can find out the area under this GC, we can find out the electron concentration. And similarly, so this is the area, okay, this is the area I've calculated. And similarly, the area under this GV, so this should be the area. If we can find out the area under this curve, what we get is the area. The area gives us the whole concentration. So you can see, as we are talking about the intrinsic, everything is absolutely similar, and the area of electron concentration and the area of hole concentration is absolutely equal. Okay. So this is the fundamental graph that latter we are going to modify when we talk about the extrinsic semiconductor. And in extrinsic, you know that either it can be N doped or it can be P doped. So obviously, depending upon the doping, we know that we are creating that imbalance. So right now, everything is balanced about this mid axis, right? So when we disturb this balance, you can see that either this area will grow large or this area will grow large, depending upon what type of impurity or what type of doping we are going to introduce over here. So this is how, again, the qualitatively we can say that fine. So and from this we can find out what could be the concentration. So now here, whatever we have earlier seen some expressions, right? Like N0 P0 is equal to Ni square, right? So we will try to prove some of the expressions which we studied in the earlier chapter. So let us start with the N0 equation. So N0, the concentration of electrons, N for electrons and 0 stands for the equilibrium. Okay, so at some thermal equilibrium, what is the concentration of electrons? And we know how to get it. We have to integrate this GC into FF, right? And when we integrate this, that is what will give us the area, and that area is nothing but the concentration of this number of electrons. Okay. So now here, as we are talking about the electrons, we know that at some temperature, the lower limit has to be EC, okay, because that is the lowest energy where it can occupy. And what could be the upper limit, or you can check here as well in the previous one. Your lower limit will be obviously EC, and your highest limit will be some energy to which there could be the number of states which are available. Okay. So the upper limit would be virtually infinity, right? So EC to infinity would be our limit for this particular integration. Okay. So now, as expected, it is evident that Fermi energy will be lying somewhere between EC and EV, and that region we call it as forbidden energy gap. Okay. So obviously, we have only validity when EC is greater than EV, and we can obviously we have already done that approximation, that if this energy difference is too greater than kT, then we can assume that if EC minus EF, that difference is too higher than kT, then obviously at any higher energy, this E minus EF should be obviously quite larger than kT, and that's why we have got this what we call it as the approximated Fermi level gap. So now this FF we have, so we can substitute it over here, and then if you remember the complete expression of GC, this is what we have got. And as we are talking about electrons, this has to be E minus EC. So obviously you can see that this would be very valid for E greater than EC, and that's why the lower limit is EC. So now the point is, if I want the number of by the way, this integration should not be there. Okay. Yeah, anyway, so if we want the number of electrons at thermal equilibrium, this is what we have to integrate. Okay, so and I think you know how to integrate this. Can anybody guess how to integrate? You might have learned one particular method which you thought that where I'm going to use it. At least I thought that when I learned particular method of integration. So that is the method I'm going to use. Okay, Shivam, any idea which integration method we can use here?
Sir, substitution method.
Yeah, of course, substitution is the most common method you use, right? Which substitution?
Sir, that
Let me give you a
E
clue, or
minus
anybody else
EF.
can answer. Let me give you a clue. It's a very special function. It's a function.
Gamma function.
Yes, absolutely right. Who answered that?
Shakir.
Yeah, Shakir. Yes, absolutely. You're spot on. Okay. So we are going to use gamma functions for that. And as Shivam has said, we have to respect him. He's coming after a long time, right? So, and he remembers that we have to substitute. Okay. So let us substitute. So let us take some n or something. Just to differentiate between normal and this is eta. Okay, so this eta we can substitute E minus EC by KT, and when you do that, obviously we know that this everything is constant, and you can take this thing out because EC and EF are also the constant, and we are talking about a particular temperature, so the temperature is also constant for us. And then when you substitute this, you will get this typical form. Okay, eta raised to 1 by 2 exponential of minus n, and then we have to change the limits, and they change from 0 to infinity, and this is a gamma function. Okay, so there is a standard outcome of this, and this is root pi by 2. Okay, so this is root pi by 2. So number of electrons right now we have is given by this particular expression. So again, root pi by 2 is constant. This is also constant. Okay, so we can rearrange the things, and then we can define this constant by NC, and this NC is a very important parameter for us. Please write it down. So our expression in shortened form will be N0 is equal to NC exponential of this bracketed term. Okay, so please write it down, and this NC is the effective density state function in the conduction band. Okay, so later we are going to use this term very frequently. We will not be writing this because so many times this concentration terms will come N0, P0, Ni, and whatnot. So at that time we are going to use this capital N, and please make a habit that you make a list of this nomenclature. Okay, because what is going to happen is the subscripts are different, superscripts are different, and there might be small letters and capital letters. So ultimately you will feel that you are looking at the same what you say nomenclature, but slight difference will have entirely different meaning. Okay, so you will see they look alike. Okay, so that's why you should be careful when you are talking about this, so that similarity is going to create the confusions later on. So that's why you should be very careful to remember the nomenclature and the definitions of this. Okay, so this is NC, and that is the effective density state function. Okay, and that is a constant now. Okay, so if you are taking T constant, and everything else is constant, so at a particular temperature, this NC will become constant. Okay, for a particular material. Okay, fine. So so we have got N0. So obviously now you can guess that similar analysis we can do for holes as well. And of course, what was our expression? N0 P0 is equal to Ni square. That is what we assumed, right? So we have derived for N0, we can derive for P0, and definitely then if we take the product of that, we know that it has to be a constant, right? So that is what the law of mass action told us. So N0 P0 should be equal to Ni square. So we can proceed for this. By the way, typical value of NC is roughly 10 raised to 25 at 300 Kelvin. That is the room temperature. Okay, so anyway, you can calculate it. So let us talk about the P0 equation. Same analysis. So again, not this. So 1 minus FF. Substitute this. This is valid for obviously E greater than EV. Again, we can do the approximation, and we can substitute this with this approximation. Now our limits will be EF is now the highest energy. Okay, so that's why it is a upper limit, and where we can go up to minus infinity, right? So everything else will be very similar. Only small change would be here and here, and instead of Mn we have got Mp. So same analysis again. We can go for the substitution over here. We get the gamma function. Okay, and then we change the limits, and that is the order of integration because of this negative sign. And when we solve this is what we are going to get. Again, the same exercise to substitute this. Now as we are talking about the holes, we can substitute by NV. Again, this is a density state function, but it is for a valence band, and this is the expression that we can get. So you can write down this expression for P0. So these are the number of holes at equilibrium, and you can see that this number of holes now dependent on the difference between the Fermi level and the valence band level. Similar thing in the previous one as well. The number of electrons will dependent on the difference between conduction energy level and the Fermi level. Okay, so this is what the importance of this Fermi level, that as we are going to change this concentration of either electron or holes when we go for intrinsic, or by some other method, maybe thermal excitation or the photo excitation, this Fermi level is going to change. It is going to adjust and all that. So Fermi level is the crucial benchmark for us. So as the concentration changes, these levels are going to change. Okay, how exactly, that we will discuss sometime later. Okay, and you can see the value of NV you can calculate. Roughly it comes out to be 10 raised to 19 at 300. So 10 raised to 25 for NC and 10 raised to 19 for the P0. Okay. So what are the important facts? Yeah, okay. Anyway, I'll stop over here. So whatever we have discussed today, I will upload the slides immediately. Please go through that in the next 2 days, so that it would be easy for you to understand whatever we are going to do. So we are going to derive so many small expressions. Okay, so that would be helpful for us later when we get the expression of current. Okay, so please go through whatever we have discussed today, and remember the important parameters, nomenclatures, and the important expressions. Okay, so thank you for today. Have a great weekend. Okay, thank you.